What if I told you that nearly 1% of the air you're breathing right now is made of a gas you've probably never even thought about? And without it, modern technology would collapse. Take a deep breath, feel the air fill your lungs. What did you just breathe in? Mostly nitrogen, you might say. Oxygen, of course. But what if I told you that a hidden passenger hitched a ride with every single breath you've ever taken? A substance that makes up nearly 1% of our atmosphere. An element so fundamental to our modern world that without it, our technological society would grind to a halt. It's not a pollutant. It's not some rare cosmic dust. It's a gas, and its name is Argon. It is the silent, unseen partner in the air we breathe and the technology we build. Argon is everywhere and nowhere at the same time. It has no color, no smell, no taste. It is completely invisible to our senses. For every 100 molecules of air that surround you right now, one of them is an argon atom. Think about that. In an average room, there are kilograms of this stuff. It slips into your lungs and back out again. A ghost that has accompanied every living, breathing creature on Earth for eons. It's an ancient, elemental part of our planet's story. We move through a sea of argon every moment of our lives, completely unaware of its presence. If you could somehow magically color every argon atom in the room blue, the air would instantly take on a noticeable, hazy tint. You'd see that this gas isn't just a trace element, it's a substantial ingredient of our world. It's more than 20 times more abundant than carbon dioxide. Yet for most of human history, we didn't even know it was there. Its discovery was a scientific surprise, a loose thread in the fabric of chemistry that once pulled, revealed an entirely new family of elements. The story of Argon's discovery begins with a puzzle, a tiny but persistent discrepancy that obsessed a brilliant physicist in the late 19th century. Lord Rayleigh, a British scientist, was conducting meticulous experiments to determine the precise density of gases. He found something odd. The nitrogen he extracted from the air was always just a tiny bit heavier than the nitrogen he produced chemically in his lab. It was minuscule difference, about 0.5%, but for a scientist of Rayleigh's caliber, it was a screaming anomaly. The universe is not sloppy. The laws of physics are precise. Something was amiss. Rayleigh was stumped. He rechecked his experiments, his calculations, his equipment. The difference remained. Was his chemical nitrogen impure, or was there something else in the atmospheric nitrogen, an unknown stowaway? He published his problem in the journal Nature, essentially asking the scientific community for help. A Scottish chemist, Sir William Ramsay, took up the challenge. Together, they embarked on a scientific detective story. They hypothesized that the air contained a previously unknown heavier gas mixed in with the nitrogen. They had to find a way to isolate it to prove its existence. To catch their ghost, they passed atmospheric air over hot copper to remove all the oxygen. Then they passed the remaining gas, mostly nitrogen, over hot magnesium. Magnesium reacts with nitrogen to form a solid. But after all the nitrogen was gone, a small bubble force, a small gas is bijvers, case was das orchid always left over. It was a stubborn remnant that refused to react with anything. It was heavier than nitrogen, and it made up about 1% of the original sample. They had found their culprit. They had discovered a new element. In 1894, they announced their finding. They named it Argon, from the Greek word argos, which means inactive or lazy. The name was perfect. Argon is a noble gas, part of a special family on the periodic table: helium, neon, saker, noxer, were not. Argon's defining trait, its profound unwillingness to react. makes it the perfect guardian. In our world, many valuable things are threatened by the very air we breathe. Specifically, it's oxygen. Oxygen is a highly reactive element. It fuels fire, it causes iron to rust, and degrades delicate materials. Argon, on the other hand, does nothing. It simply gets in the way. By replacing the reactive air with inert argon, we create a protective bubble, an invisible shield. This principle is fundamental to welding. Imagine a welder joining two pieces of steel. The intense heat of the welding arc melts the metal, fusing it together. If that molten metal were exposed to the oxygen and nitrogen in the air, it would react instantly, creating oxides and nitrides. These impurities would make the weld brittle, weak, and porous, a catastrophic failure waiting to happen. To prevent this, welders use a technique called gas metal arc welding. A stream of argon flows from the welding torch, blanketing the molten metal pool. The argon pushes the air aside, forming a tiny, localized and unreactive atmosphere right where it's needed, ensuring a strong, clean and durable bond. This same principle of protection extends far beyond the workshop. Think of priceless historical documents like the United States Declaration of Independence or the Magna Carta. For centuries, they were stored in air, slowly yellowing and fading as oxygen and moisture took their toll. Today, these irreplaceable artifacts are preserved in specially designed cases filled with pure argon. The argon gas displaces the destructive oxygen, halting the chemical reactions that cause decay. While argon is known for being inactive, it can put on quite a show when you give it a little energy. You've probably seen signs that glow with a brilliant, captivating light. Many people call them all neon signs, but that's not quite right. True neon gas glows with a fiery, reddish-orange color. For other colors, sign makers use different gases. Argon is a star performer. Seal argon in a glass tube and pass a high voltage electric current through it. Its atoms become excited, and as they return to normal, they release that energy as light, a soft violet blue glow. By mixing argon with a little mercury and coating the tube with phosphors, artists can create a whole spectrum of colors. This ability to glow made argon essential to one of history's most important inventions, the incandescent bulb. The classic bulb works by heating a thin wire or filament until it glows white hot. In the open air, that filament would vaporize in an instant. Early bulbs had a vacuum inside, but the filament still slowly evaporated and deposited black soot on the glass. The solution? Fill the bulb with argon. The inert gas creates pressure that suppresses evaporation, allowing the filament to burn hotter and much longer, transforming our world from one of darkness to one of light. But argon's most critical modern role is arguably in the creation of the very brains of our digital world, the semiconductor. The microchips in your phone, your computer, and your car are marvels of engineering built layer by atomic layer in ultra-sterile clean rooms. The slightest speck of dust or a single stray molecule of water or oxygen could ruin an entire batch of chips. To create the purest possible environment, manufacturers use argon to purge chambers and protect a wafer of silicon as it undergoes dozens of manufacturing steps. Argon is also used in a process called sputtering, where argon ions are accelerated into a target material. Those ions knock off atoms that then deposit as a thin, uniform film on the silicon wafer. This is how the microscopic wiring that connects millions of transistors on a chip is created. Without an impeccably pure, non-reactive gas like argon, the mass production of reliable, powerful microprocessors would be impossible. Every time you send a text, watch a video, or browse the internet, you are using a device that could not exist without the help of this invisible lazy gas. So, if argon is all around us, mixed into the very air we breathe, how do we get it out? We can't just scoop it up with a net. The process of isolating argon is a testament to our understanding of the physical properties of matter, and it happens on a massive industrial scale. It all begins with the air itself. Huge facilities known as air separation plants are essentially giant high-tech distilleries. Their raw material is the free and abundant atmosphere. Their first step is to turn that air from a gas into a liquid. To do this, the air is first filtered to remove dust, water, and carbon dioxide. Then it is compressed to incredibly high pressures and cooled to cryogenic temperatures far colder than any freezer on Earth. It is cooled down to below minus 183 degrees Celsius, minus 297 degrees Fahrenheit, the point at which oxygen liquefies. At these extreme temperatures, the familiar invisible air we walk through transforms into a pale blue, shimmering liquid, a mixture of liquid nitrogen, liquid oxygen, and our target, liquid argon. This frigid cocktail is the key to separating the components. The process used to separate them is called fractional distillation. It works because each component of liquid air boils at a slightly different temperature. The liquid air is pumped into the bottom of a tall distillation column. As it is slowly warmed, nitrogen, minus 196 degrees Celsius, boils first and rises to the top. Oxygen, with the highest boiling point, minus 183, stays liquid at the bottom. Argon's boiling point is minus 186, where base nestled right between, so it concentrates in the middle. By carefully controlling temperature and pressure, technicians draw off an argon-rich stream, then purify it in a second column to reach 99.999% or higher. It's an energy-intensive and highly technical process, taking a ghost from the air and bottling it for our use. Beyond its industrial might, argon has a few more surprising roles to play. In the world of deep-sea diving, it has found a niche use. Because argon is inert, it doesn't cause the intoxicating effects of nitrogen narcosis at great depths. It also has low thermal conductivity, meaning it doesn't transfer heat very well. For this reason, some technical divers use pure argon to inflate their dry suits. The dense, non-conductive gas acts as a superior insulator against the crushing cold of the deep ocean, a thermal blanket protecting the diver from life-threatening hypothermia. In the realm of fundamental science, argon is helping us hunt for the most elusive particles in the cosmos. Deep underground, shielded from cosmic rays, physicists have built enormous detectors filled with thousands of tons of ultra-pure liquid argon. Experiments like the Deep Underground Neutrino Experiment, DUNE, use these vast, cold, and clear vats of argon as targets for neutrinos. When a ghostly neutrino, which can pass through planets' esfuerzos, happens to strike an argon nucleus, it creates a tiny flash of light and a trail of electrons. By tracking this faint signal, scientists hope to unlock the deepest secrets of matter and the universe. So, here are a few more facts to ponder. Argon is about 38% heavier than air, which is why it can be used to displace the atmosphere and settle like a blanket over wine. The purple glow of argon in a plasma ball is one of the most common demonstrations of its energetic state. And despite being called lazy, argon compounds have been created in labs under extreme conditions, proving that even the laziest element can be prodded into action, if only for a fleeting moment. It's a reminder that the universe is always more complex and surprising than we think. Argon is the quiet element. It is the third most abundant gas in our atmosphere, yet it passes through our lives and our lungs largely unnoticed. It doesn't give us life like oxygen or form the backbone of life like carbon. Instead, it protects, it preserves, it enables. It's the invisible infrastructure supporting our brightest lights, our fastest computers, our most precious history. It's a humble gas, distilled from the air, that has become an indispensable pillar of the modern world.